All right, today we're going to go over aircraft performance and some of the different tables and charts that you'll use to calculate performance. Some of these are going to be exactly what you would use for the Cessna to calculate performance for like a cross-country flight or something. Other ones are going to be less common, but they will definitely show up on your written test, and so you need to get familiar with them even though you don't exactly use those for your flight training. So, importance of performance data, understanding aircraft weight, which we talked about last time, atmospheric conditions, runway environment, and some of the fundamental laws like aerodynamics that are affecting the aircraft. The performance section in the POH is what typically you would use to calculate all of this. That's going to include takeoff performance, which means how long of your runway do you need to take off. Your climb performance, so how long can you expect it to take you to get to your cruise altitude. Range and endurance, which we'll talk about. Descent, which Cessna does not include in the performance section, and landing performance. Some of the tables that we'll look at are under certain conditions, and I'll show you each of them have notes associated with them, and it'll have the conditions in which that aircraft was tested. So you want to look at those notes and also keep in mind that these tables that we're going to look at were performed by a test pilot. So the skill level may be a little bit different. The aircraft may be a little bit newer than what you're flying now. So there is going to be some margin of error. And we've looked at this slide a few times, but talking about aircraft performance, it's a good reminder, looking at composition of atmosphere and how density changes with altitude. Again, there's going to be a little bit of a review. So things that affect pressure are going to be your temperature, humidity, and altitude. And as just a review, you have your standard measurements. So at sea level, standard temperature, 15 degrees Celsius, standard pressure, 29.92, and our standard lapse rate. So decrease of 2 degrees Celsius for every 1,000 feet and decrease of 1 inch of mercury for every 1,000 feet. And another look, we already talked about these things that affect air density, but just comparing this to a performance table that you'll come across. So pressure is going to affect your air density. So as you go higher up in altitude, there's less air pressure. Air is able to expand and spread apart, so air becomes less dense. Temperature, as the air heats up, molecules move a lot faster, they spread further apart, air becomes less dense. And humidity. So water vapor displaces air molecules, and so air can't occupy as compact of an area. As we're talking about performance, the reason why we want to calculate performance and consider how density affects it. So power is going to be reduced. As air density decreases, you have less air being mixed with fuel. So overall, you're going to produce less power. You're going to produce less thrust. So as your propeller blade is spinning, there's going to be less dense air having an effect on that propeller blade. And lift, so air that's interacting with your wing is going to be less effective at producing lift. Pre-decom and checkride question, everything on the slide right here. So you would definitely be asked about how density affects performance. And so you want to be able to explain it. And just to review, we already looked at these when we talked about flight instruments, but now we're taking into consideration aircraft performance. And when we fill out a navlog, which we'll talk about with cross-country flight, is we're going to use all of these different airspeeds for cross-country planning. So your true airspeed is basically the speed at which you're flying through the air. So if you were to fly through a mass of air, how fast are you passing that air mass? Your calibrated airspeed is your indicated airspeed, accounting for instrument errors. And less commonly used is equivalent airspeed. So it's going to be your airspeed indicator corrected for position or installation error. Stall speeds again. So VSO is going to be your calibrated stall speed with your flaps down, which is the bottom of the white line. And then your VS1 is going to be the bottom of the white, or bottom of the green, sorry. So really good visual comparing VY and VX. So VY is going to be your best rate of climb, meaning you can get the most altitude in a given amount of time. So if you were to set a timer for each of these airplanes, VOI would get to 1,000 feet sooner. Now if you're just measuring horizontal distance from the runway, VX would get to 1,000 feet sooner than VY. We'll use both. For the most part, most of your training is going to use VY for takeoff speed. It's a little less steep, but overall it's going to get you the most altitude in a shorter amount of time. And when you get into stage 2 and learn how to do short field takeoffs or takeoffs like over an obstacle or simulated obstacle, I'll call it, you'll do VX climb. Same power setting, you're just climbing at a steeper angle. In other performance limitations, landing gear we're going to skip over because we have fixed gear. FEE, flap extension speed, is the white arc. So as long as you're flying within this white arc on the airspeed indicator, you can extend your flaps. Maneuvering speed will not be indicated on your instrument, and that's something that has to be calculated before your flight. So you have to calculate weight and balance, refer to the POH for what your maneuvering speed will be for that given weight. VNO, max speed for normal operation, and VNE, never exceed, which is going to be this red line right here. So I mentioned these altitudes before, but we're going to actually try to understand them a little bit more. Pressure altitude is your height above standard datum plane. So what that means is if you were to set your altimeter to standard 29.92 and refer to your altimeter, whatever it tells you on the instrument face is your pressure altitude. So if you're sitting on the ground at John Wayne and you set the pressure setting to 29.92, whatever your indicator tells you, that's your pressure altitude for that given moment. A few ways to do that. First one, like I said, is setting your Colesman window to standard 29.92. Other one is kind of a formula method. So you take standard 29.92, subtract the current altimeter setting, multiply that by 1,000, and then add your elevation. So it could be field elevation. If you're on the ground, it could be your cruise altitude for elevation. Lastly is using a flight computer or an E6B. That's this little device here at the bottom right. And as a reminder, if you don't have one of these yet, I'd recommend picking one up. We'll be using it pretty soon. Now, density altitude. So your density altitude is taking the pressure altitude that we just talked about and adjusting it for non-standard temperature. So temperature is never going to be completely standard. It's never going to follow standard lapse rate perfectly, and so we need to be able to calculate accurately what density altitude should be. So the phrasing of density altitude generally confuses people. So when we say high density altitude, that means low air density. When we say low density altitude, that means high air density. If you can just picture high density altitude is equivalent to high altitude, it makes a little bit more sense. Commonly, we always use Big Bear. So Big Bear during summer generally has high density altitude. So right now, the density altitude of Big Bear is about 9,000 or 10,000 feet. So the airplane is going to act, or it's going to perform like it was at 10,000 feet, which is very poorly. So the performance, the power output is going to be very poor, and the amount of lift and thrust you're able to produce is very low because it thinks it's at 10,000 feet, even though the field elevation is like 6,700 or something like that. So there's a few ways to calculate that. Again, using the flight computer, you can also calculate density altitude. Using a conversion table, which is what this image is right here. You'll most likely use this only on the written test. So like the Cessna POH won't have a conversion table in it, and I'll show you why. So on the written test, you'll be given a table like this, and it will ask you to calculate density altitude. Number 3 says performance charts. So some performance charts provide different tables for given temperatures. And so you would just round to the nearest temperature and use the performance numbers from that nearest temperature. The other one's formula method. So density altitude is equal to pressure altitude plus 120 times outside air temperature. That's what OAT means. Minus standard temperature. So what that means is current temperature minus what it should be for that altitude. So actually, while we're talking about number 4, we can go over a quick scenario. So let's say your pressure altitude is 6,000 feet. So let's do 6,000 plus 120 times, and let's say the outside air temperature is, I'll I gotta do it in Celsius. Let's say 28 degrees, which is pretty warm for that altitude, but not uncommon. So last week it was 30 degrees at 4,000 feet, which is about 95 degrees. So it was an inversion. So on the ground, it was like 80 degrees Fahrenheit, and then you go up to 4,000 feet, and it was 95 degrees Fahrenheit, which is weird. All right, so 6,000 feet pressure altitude plus 120 times 28 degrees Celsius minus, and that leads us up to what should the temperature be at 6,000 feet given standard lapse rate. So it's 15 degrees Celsius at sea level, and it should decrease 2 degrees Celsius for every 1,000 feet. So some considerations with density altitude. So let's say you do go to an airport that has high density altitude, and another consideration is maybe you're at max weight for the aircraft. You know, you took a couple of your friends to a high density altitude airport. It makes it very difficult to depart from that airport. You may be able to land there, but it may be more difficult to depart, especially if there are obstacles or like high mountains around this airport. And so as a private pilot applicant, you want to be able to think about what can you do to mitigate risk in this case. Wait until the density altitude decreases, and so wait till the temperature is lower. So that could be wait till the next morning. A common thought is, oh, just wait till it's dark. Again, you're going to fly at nighttime through mountains, which is generally kind of dangerous. Best case would be wait till the next morning. Especially as the sun's coming up, you'll have daylight. It's easier to see. It's going to be cool, and so density altitude will be a lot lower. Considering performance, it generally describes the effectiveness of the aircraft to accomplish what it is designed to do. We've looked at this considering like aerodynamics and stability. The same thing applies for performance. So each one of these aircraft are going to perform differently. They're generally very good at their particular job. So like in a Cessna, we can't fly very fast or maneuver very easily. Same thing with an airliner. It's meant to carry a lot of cargo over long distances, but it's not very nimble, if that makes sense. Whereas something like an aerobatic aircraft or a jet fighter can usually maneuver pretty easily. So looking at some examples of climb performance tables, we already looked at VX and VY. And these are some examples of tables from Cessna. So this first one here in the middle, maximum rate of climb at max weight, which is 2550 for an S model Cessna. So given the pressure altitude, so if you're departing from sea level or near sea level, you would climb at 74 knots indicated, and given whatever temperature is closest, so let's say 20 degrees Celsius, you'd be able to climb at 710 feet per minute. And another common table that we will look at and use is time, fuel, and distance to climb. So the way you'd use this is going from sea level to, we'll just use 6,000 feet again, is you would go sea level to 6,000 feet, you would climb at 73 knots indicated, 505 feet per minute. It's going to take you 10 minutes and 2.2 gallons and 13 miles to get up to 6,000 feet. So if you were to maintain this airspeed, this is the performance you can expect to go from sea level to 6,000 feet. So this is one of the tables you'll use for cross-country flight. An important note right here at the bottom, it says add 1.4 gallons of fuel for engine start, taxi, and takeoff allowance. And comparing service ceiling and absolute ceiling. So service ceiling is density altitude, which the aircraft's unable to climb at a rate greater than 100 feet per minute. And absolute ceiling is basically the highest the aircraft can climb, so it's unable to climb anymore. I mentioned these ones before, range and endurance profiles. These are other tables from the Cessna POH. So range is talking about how far you can fly in nautical miles. The way you'd use this table is look at your altitude and compare that to your power setting. So are you using 75% power, 65%, 55%? And where those two plots intersect, so let's say 6,000 feet again at 75% power, then you drop straight down, and that'll tell you how far you're able to fly. So in this case, 520 nautical miles, which is pretty far. So by reducing your power, you're able to fly a little bit further. And this is an example of true airspeeds that are going to be used at that power setting. Chart presentation. So I mentioned conditions before. So at the top of most of these charts will be a set of conditions in which these performance tables were calculated. So for this example, a short field takeoff at max weight was done with flaps 10 degrees, full throttle, prior to brake release, and it was done on a paved level dry runway. Reason why they have to mention that almost as a disclaimer is if somebody is trying to take off with no flaps, partial power on like a grass runway or something, they can't expect to get this kind of performance in those conditions. But always look at the conditions. Sometimes we'll look at a different table, and sometimes it'll advise you to either add or subtract distances for takeoff or landing, depending if there's headwind or tailwind. Another look at takeoff distance. So the way you would use this is pressure altitude, in this case 4,000 feet, and the nearest temperature. And where those two intersect, that's going to give you your ground roll, so 1,440, and your total distance to clear an obstacle. So it's kind of cool to note, if we are at sea level in cold conditions, so that's low density altitude, your ground roll is only 860 feet, and your total distance to clear an obstacle is 1,465. So it's a pretty short distance. So if we were to try to depart a higher altitude, 8,000 feet, on a hot day, it's 2,400 feet ground roll and almost twice that amount for clearing an obstacle. So it kind of gives you a visual that your takeoff performance is much flatter. You're not able to climb at the same angle that you would for like sea level on a cold day. So that's something people don't anticipate, especially if they're departing a high density altitude airport that has obstacles. And when I say obstacles, usually it's trees or buildings, or maybe mountains on the sides of the runway. And so they don't anticipate, if they hadn't calculated takeoff distance, they don't understand how long it's going to actually take them to clear that obstacle. And so they usually end up flying into the obstacle because they're flying very shallow or very flat. Everyone's favorite, graph format. So these are typically going to be only seen on your written test or if you fly a Piper. We'll go over an example, but this is incorporating a few different performance tables into one. So you will usually be provided the temperature and your pressure altitude for a question like this, and the way you use it is find your pressure altitude on these black lines and your temperature here at the bottom, and where those two plot points intersect, you go straight across horizontally, and this red line is just showing an example. And then the next category is your weight. So if the aircraft were 2,600 pounds, you would continue this red line straight across until you intersect 2,600 pounds, and then you track parallel to those black lines. So those black lines are reference lines, and you follow them parallel until you get to your weight, and then you go straight across, and that gives you your wind component. And you can see there's a headwind tab and a tailwind tab. So if you had a tailwind, you would track the dashed lines upward. If it's a headwind, you track these black lines downward. We'll go over an example. It'll make a little bit more sense. I know it's kind of nonsense at this point. So in the case of this example, the red line tracked downward until it intersected the wind component, and then it goes straight across horizontally. And then this next category is your obstacle height. There's no intermediate obstacles. It's either there's no obstacle or a 50-foot obstacle. Those are your only two choices. So if there's no obstacle, you just continue straight across, and wherever this plot ends up, that's going to be your takeoff distance. If there is an obstacle, you use these guidelines, the black lines, and track that upward. And where that ends up is going to be your total distance to clear that obstacle. Like I said, we'll go over an example. My tips for this one, bring a magnifying glass. I'm just kidding. Use a straight edge. It's going to be the easiest thing to do. Sometimes people try and freehand it or like visualize. And even a small error kind of on the first section right here is going to lead to like a much bigger error on the right side. So use a straight edge. Use a plotter. You could use the straight edge of the flight computer if you want. You're not allowed to draw on the supplement book you're given on the written test, but they'll give you usually like a plastic sheet or cover and a dry erase marker, and so you can use that to draw on it. All right, first practice question that we're going to look at is this density altitude conversion table. I want to start with saying the right side of this table, so these green columns, this is only to get to your pressure altitude conversion. So it says conversion factor because you either add this number to your starting altitude or you subtract it if it's a negative. So the right side of this is only to get to your pressure altitude, and the left side of this table is to get to your density altitude. So there's two steps to it. So the first step is on the right, second step is on the left. So you want to pay attention to the wording of the question. If it's only asking pressure altitude, you don't need to end up on the left side. If it is asking for density altitude, you need to first get pressure altitude and then density. Your first step, we haven't talked about it yet, is this one will require something called interpolation. And so you're finding the average between two different points. Luckily, this one is fairly easy because the point it's asking for is 30.35. If you look to this table here to the right, we don't have that. We have 30.3 and 30.4. So we need to find the number that's in between those. So it's going to require interpolation. So average those two. It's a 92-foot difference between these. Divide that by 2 to find the midpoint, and you get 46 feet. So you can either subtract 46 from 440 or add it to 348 to get that. So you should end up with negative 394. So then you subtract that. Since it's a conversion factor, any of these negative numbers you subtract from your original elevation. So our starting point, 3,894 minus 394, should give you 3,500 feet pressure altitude. So that's the first step. So we take that information and then find 3,500 feet on the left table. So these black lines that are kind of going diagonally is your pressure altitude. Runway temperature was 25 degrees Fahrenheit. So you find 25 degrees Fahrenheit here at the bottom. Trace that straight up until it intersects 3,500 feet. So here's 4,000 and 3,000. So this should be your pressure altitude line right here. And there's that plot point. So from there, you go straight across to the left, and you should end up at 2,000 feet of density altitude. So it takes a little bit of work to get the answer, but most common mistakes I would say is reading the question carefully. So if it were just asking for pressure altitude, then the answer would be 3,500 feet. Since it's asking for density altitude, we need to go to the second step, which is this side over here. Takeoff and landing performance. So we showed a few takeoff tables. Few short field takeoff tables. One of the differences is going to be weight. So you have a few options in the Cessna POH, which is another reason why you'll need to calculate weight and balance. So performance at 2,400 pounds versus max weight 2,550. And you can just compare the distances. So only 150 pounds of difference, comparing that to your takeoff distance here, 2,400 versus 2,000. At a high density altitude conditions, it's going to save you 400 feet of distance, or 900 feet for obstacle clearance. So 150 pounds translates to 900 feet of obstacle clearance. Kind of significant. And another table format that you'll see on the written test would look like this. And they'll give you certain conditions, and the question is saying determine the approximate landing ground roll distance. So let's take a look at that one in your supplement book. So using the given conditions, sea level, headwind 4 knots, and temperature standard. Luckily this one's pretty simple, there's only one row of information. And it says sea level, so at sea level we're going to use this block of information here. And it's only asking for ground roll distance, not obstacle clearance, so we'd look to 445. So ground roll is 445, and if you look at the notes, decrease the distance as shown by 10% for each knot of headwind. So 10% of 445, and then you subtract that and get 401. Surface winds or wind component is, you will see this table. So you'll see this table in the POH. Some knee boards have it printed on it as well, so you can calculate that as you're flying. So the way you use this is you calculate the difference between the wind direction and your landing runway, I guess, heading, or the angular difference between the runway and the wind. So if the runway is 200, like it is here, and the wind was reported 170 degrees at 20 knots, find the angular difference, so 30 degrees. Then you find 30 degrees on this arc right here. Next step is to find the velocity, which was 20 knots. So here's 20, and there's that arc right there. So where the 30 degrees and 20 knots intersect, go straight down, that'll provide your crosswind component, 10 knots. If you go to the left, that's going to provide the headwind component, which is about 18 knots. So just because the wind is reported 10 knots, 20 knots, 30 knots doesn't mean it's a direct crosswind or necessarily dangerous. 20 knots of headwind would probably be very helpful for landing or takeoff. 20 knots of direct crosswind is not the most safe. So you just want to consider how much of that is going to affect your landing. So how much of it is crosswind component or headwind component. So ideally you'd have reserve. You can go land somewhere where it's less significant. Or even if the wind is just as strong, maybe it's less of an angle at some other airport. So it's not necessarily a limitation, but in the Cessna POH, its maximum demonstrated crosswind is 15 knots. That doesn't mean it's a limitation. It doesn't say don't go fly with more than that, but that's what a test pilot was consistently able to use. So looking at this, 15 of direct crosswind, that could be 30 knots of wind coming from 30 degrees, and that translates to 15 of crosswind. Or it could just be from 90 degrees, and that would be 15. Yeah, because there comes a point where you're not able to control the aircraft laterally across the runway. You can't hold center line anymore. So you kind of run out of rudder authority, and it becomes unsafe. Another consideration is runway gradient. So if you look at the chart supplement, it'll provide runway information. So if it's paved or not, if the runway's grooved. So like our runways here are grooved, so it allows rainwater to get off the runway. And it'll also provide gradient, so 1% down, 1.1% up, and that's also going to affect your takeoff and landing performance. So if you're trying to take off uphill, it's going to require a little bit longer of a distance. If you're landing downhill, generally you're going to float for a little bit longer. Also going to affect your brake performance as well. So just another thing to consider when you're flying to an airport is do your research, understand all the aspects that are going to affect your performance. All right, here's a fun one. So figure 37, determine the approximate total distance required to land over a 50-foot obstacle. So our starting point here on the left, we were given outside air temperature 90 degrees Fahrenheit and pressure altitude 4,000 feet. So there's 90 degrees, and then you can track that straight up. There's 4,000 feet of pressure altitude, so you trace these black lines parallel until you get to this intersect point right here with your temperature. So where those two green lines intersect, then you go straight across horizontally until the next reference line. And then from the reference line, you're going to track these black lines parallel at a down angle until you get to your weight. So our provided weight was 2,800 pounds. Don't have to trace it very far, but track these parallel until you get to 2,800 pounds. It's kind of confusing too because they pick references that are very close to the red lines, which they use as the example, and so it's hard not to want to follow those ones. And then once you reach 2,800 pounds, you can go straight across to the next reference line, and that brings you to your wind component. So wind was headwind component 10 knots. So here's the label for headwind. It means you're going to trace this downward along the black solid lines until we get to 10. So here's 10. Then you go straight across again. And the question was asking for a 50-foot obstacle, and so that means you're going to trace these reference lines upward. So you should reach that point right there, and that'll give you 1775. So this is pretty difficult to read. So here's 1,500. This middle point should be 1750, and then there's 1775. So if there's no obstacle, you go straight across like the red line. If there is a 50-foot obstacle, then you track parallel to these black lines. So those are the only two options. It's never going to give you a 30-foot obstacle or 100-foot obstacle. It's only going to be 0 or 50. So this is the information for the red lines right here. So 25 degrees Celsius, pressure altitude. Again, they're very close to the example that we used. And 9 knots of headwind, whereas we used 10. So a lot of these figures are pretty close. Cruise performance table. So use it just the same way you would the other ones we looked at. Find your pressure altitude. So if our cruise altitude is 6,000 feet, our next step is to find the conditions. So 20 degrees below standard temperature, standard, and then 20 degrees above. And do you want to look at the note here? Maximum cruise power using recommended lean mixture is 75% max cruise power. So you generally want to operate below 75% of your max cruise power because you don't want to have a high RPM setting for a prolonged period. So let's say we're at 6,000 feet in standard temperature. The numbers on the left are your RPM. Next to that is going to be your cruise power percentage right here. So 77, obviously you don't want to use that for prolonged periods. 73 is still below it, but in my experience it's still kind of high to hold that for 1 or 2 hours. I'd say average, most people use about 2,400, 2,500 RPM for cruise, at least in the aircraft that we use. So let's say we're using 2,500 RPM. Then you'd find that along the standard temperature table right here. So that's 65% of your max cruise power. Your true airspeed at that power setting should be 114 knots, and you're going to burn 9.0 gallons per hour. So that's where you would pull that information from when you're calculating performance information. So how long is it going to take you to get to your destination? You already know how fast you're going from this table, so you can use that to calculate. And how much fuel are you going to burn? So that would all be used from this table. All right, another one we'll look at, figure 35. These ones aren't very helpful to talk about. It's more helpful to kind of get your hands on them and practice. So first thing we look at, pressure altitude. And that's going to be found on the left here is 8,000 feet. So it's going to be anything along this row. And then our temperature, 22 degrees Celsius. So here's your indicated outside air temperature for each of these. So we're trying to find 22 degrees. So this one's minus 19, 2, there's 22. So the information we need is going to be along this row right here. So the only information you actually need, since it's asking for fuel burn, is your gallons per hour. And one thing that generally trips people up is your eyes automatically go to miles per hour, because that's what everybody's used to. But since we are in an aircraft and we're using nautical miles, it's going to be knots. So there's your gallons per hour, 11.5, and your airspeed is 164 knots. So we can use that in order to calculate our fuel burn. So 1,000 nautical miles divided by 164 knots is 6.1 hours. That, along with our fuel burn, 6.1 times 11.5 gallons, which we got right here, gives you 70.1 gallons of fuel consumed. So that'll be answer B.